Hello, good afternoon, everybody. This is the fourth day of this webinar on the CO2 refrigeration system, fundamental advancement and applications. So today we had three lectures, starting from this the total thermal energy storage with CO2 by Dr. Hakon Selvnes from SINTEF Energy. That is followed by Dr. Kristina and Professor Sheshadri from IIT Madras. So I'll just introduce about Dr. Hakon Selvnes. So Dr. Hakon Selvnes is a research scientist in the SINTEF Energy Research in Trondheim, Norway. He has his MSc in mechanical energy with a specialization in refrigeration and heat pump from NTNU, Norway. In his PhD research project at NTNU, he investigated, developed, and demonstrated cold thermal energy storage technology with phase change material for refrigeration system. Currently, he involved as a researcher and project leader in government-funded and industry-funded research project on energy efficiency, heat pumps, and refrigeration technology. So now, Dr. Hakon, the floor is yours now. You can continue your talk. Thank you.
Thank you very much for the introduction. I'll try to share my screen here now. I have to apologize in advance. I have gotten a bit of a cold over the last few days, so I apologize if my voice doesn't hold through all the way through, but I will try the best I can to get through it. So can I get a affirmation that my slides are visible now? The screen is visible?
Yes, your slides are visible. And can you put on the full screen mode?
I think so. Just a second. Maybe I shared the wrong screen. It should be this one.
It's a presentation mode, and we could see your notes and the next slide. So
you see still see just my PowerPoint, not the full slides. Try to share.
Are you sharing a screen with?
I'm trying. Just a second. About now? Still see the PowerPoint or see the slides?
We can see your entire screen. It's not in presentation mode right now.
Are you correct form or are you in the full? I'll then I will share my screen instead. Let's see.
Share your entire screen otherwise.
Into share. And but now?
Now it is fine.
Okay, thank you. Sorry about the delay. So welcome to this talk. First, I would like to thank for the opportunity to come and give a lecture on this topic of cold thermal energy storage with CO2. In this talk, I will touch upon an introduction to cold thermal energy storage, what it is about, focusing on CO2 refrigeration system, but also with CO2 as a storage medium. So this is the outline of the presentation. I will start with some introduction and motivation on why this topic is important for CO2 refrigeration systems and refrigeration in general. I will go through some of the basic and the concepts behind the technology and also the phase change materials, which is the medium that we store the thermal energy in. Then I will go through some technology and applications of cold thermal energy storage, some future perspective, and a quick summary at the end. First, I would like to say just a couple of words about where I work at SINTEF Energy. SINTEF as a whole is a world-leading research institute, so it's an independent, one of Europe's largest independent research institutes, It's operated on non-profit basis. That means that all the income that we generate from projects with industry, governmental funded projects, etc., it's reinvested into lab infrastructure and in this case advancing our position as a research institute forward. We have about 2,200 employees. It's only in Norway, spread across cities, based in Trondheim and Oslo for the most part, and we carry out about close to 7,000 projects every year within the organization. We also are very attractive international among our international employees, so we have about 88 nationalities currently in the workforce. We in SINTEF we do research within a large sphere of projects spanning from industry and construction in the competitive range to the societal research. So we research mobility, secure societies, health and welfare, etc. And the center of it all is the climate and environment. I work at the Department of Energy Research, and we focus on the future energy solutions, both for globally, for Europe in particular, and especially for Norway, to make Norwegian industry and energy systems as competitive and be the showcase for the rest of the world. All our projects have to be based and marked with the UN sustainability goals to ensure that all our activities are in the best interest in our planet and our society. So in SINTEF Energy, at least, most of our projects are related to these five sustainability goals: clean energy, climate action, and also sustainable cities and communities in particular. Our strategic focus is energy efficiency, where I belong, where I work mostly in heat pumps and refrigeration systems, but we also span across multiple other topics like hydropower, bioenergy, hydrogen, zero emission transport, etc. So it spans, and we have also this picture in the background is the high voltage laboratory in Trondheim, where we do high tests of components at full scale. So let's get back into the topic of called thermal energy storage. The reason why we are invested in this kind of topic is that we know that space cooling, for instance, is one of the fastest growing end use of energy in buildings. And we project that air conditioning will constitute up to 50% of peak electricity demand, especially in warm regions where India, particular, and the Middle East are driving these numbers up. This graph here is taken from the International Energy Agency report of future of cooling, which shows that share of electricity load, peak electricity load in different regions. In the light blue here is the 2016, and the baseline scenario towards 2050 is the darker blue, and also an alternative scenario with more efficient air conditioners. But we see that for instance, taking India as an example here, it's less than 10, or it's around 10% today, let's say for a couple of years ago, but it's spiking quite fast, and the growth is coming the next year as well. More people are getting access to better comfort and etc. So this is something that we have to tackle, especially in regions where the electricity grids is not well established. So we need to find solutions that will help us mitigate this kind of effects with peak power load, because this is very challenging for the future power grid. Along the same path, we say that, okay, this is also fueled in terms of the increase in renewable energy as the total share of the power mix. And we know that if we are going to reach the 1.5 degree goals defined in the Paris Agreement, renewable energy has to be the main source of electricity. And this solar and wind in particular are intermittent energy sources, and there will be a large need for flexibility in the future power grid in order to handle this kind of nature of the power sources. So the EA also estimates that we need here is mentioned battery storage by 40-fold towards 2040, but also thermal energy storage, not only electrical storage, will be very important in this scenario, because we know that for industry and we know that the energy is required in the form of thermal energy. Most heating and cooling, not electricity as such, it's just used and then converted to heat. So we could mitigate this kind of effects by going to store the energy as a thermal energy instead. And also for business opportunities, is a very interesting case. There's an estimated market of 300 billion euros for thermal energy. That's thermal energy storage. So a bit more into technology and how does this work. I'm taking here a generic refrigeration load as an example. The dark or the black curve here is representing the refrigeration load of a refrigeration system during one day. And if there was no storage integrated into this refrigeration system, the chiller or the refrigeration plant had to follow the load curve exactly throughout the day. That means that our capacity has to be dimensioned to the maximum peak of the refrigeration load. In the case that we have thermal energy storage, or called thermal energy storage integrated, we are allowed to decouple the supply and demand of thermal energy or refrigeration load. So in this region C here, the storage is charged by the refrigeration system because we have excess capacity compared to the load. So we use this time to store energy in the storage, and then at a certain point we might want to turn off the refrigeration plant and cover the entire peak by the storage, and at a certain point also turn off again. This is the extreme scenario, or what we call the full storage scenario, or the principle, where everything is covered in the peak hours, covered by the storage. So we turn it off, the chiller, completely. A different method of operation or strategic way to operate the storage combination with refrigeration plant is to dimension the storage and refrigeration system together to be able to run the refrigeration system at a constant load throughout the day. So this requires a very good overview of the thermal demands in your process. It means that you have enough storage capacity to cover the load, and also enough capacity of the refrigeration plant to be able to charge the system during off-peak hours. So this is an interesting scenario where you can dimension your refrigeration system very close to the average roll load rather than the peak load. Some sort of a middle ground would be what we call partial storage with load limiting. That means that, okay, maybe you want during peak hours only to draw a certain power from the grid. Means that you reduce your capacity of the chiller during these hours while you cover the rest of the refrigeration peak load with the storage. So in economic sense, the full scenario will probably be way too expensive because you need both high chiller capacity and a large storage in order to cover the peak. This one is interesting from optimization of operational point of view, but this one is probably the most likely scenario and the most economic scenario, where you let's say you want to keep under a certain electricity power peak tariff to avoid certain fees during peak hours. So that could be some economical benefits in that. Okay, so that's well and good. So why is it a good idea? I mentioned some of the points already. So why is it a good idea to implement thermal storage into refrigeration systems? For once, it's to reduce the required compressor capacity. So the compressor capacity that you have to purchase in order to meet the peak load of your refrigeration system or your process plant or whatever is the what needs cooling. Could be air conditioning, could be process cooling, could be freezing of food, etc. But if you invest in the storage, then you can reduce the compressor capacity and you're able to operate closer to the average load rather than the peak load. Linked to this is that you shift the peak power demand from the grid to off-peak power hours. That means that you reduce the maximum demand that you need from the grid. In Europe, at least, that translates into lower peak power tariff fees for the operator and user. Another point is that you have a backup in case of one compressor. If you have a multi-compressor pack, you have one compressor failure, and then you have some certain thermal backup in the storage until you get fixed or replace the compressor. So you are able to supply more peak power or peak refrigeration capacity, even though you have a machine failure. You reduce the hours in partial load operation in the plant, which is partly linked that you design your system to be operate closer to the average load rather than the peak load. Most refrigeration systems today have some sort of peak or let's say off part load mitigation strategy, meaning variable speed drive, cylinder offload regulation, so things like this. But it's no secret that the energy efficiency is highest at the design capacity, which means that is the peak capacity in conventional systems. But with the storage, you can operate closer to the average load. Additional, you can subcool refrigerant in the system, which can be process improvement, exploit some hours of the day where electricity is of lower cost. For example, during the night, when you charge the system, you will spend more electricity in the night and off-peak hours rather than the peak hours. And for supermarket refrigeration systems, it's often a challenge with a lot of on-off cycling during the night when there's no people in the shop, when the doors of the display cabinets are locked. There's not much load, but the compressors turn on and off during the whole night. And if you have a storage, you can reduce this on-off storage on-off cycling because you are introducing load to the refrigeration system while you're charging. So these are some of the benefits that you can get from integrating storage. So then there's a point of the strategy that you use for the actual storage of energy. We have two different principles. It's the sensible thermal energy storage or the latent thermal energy storage principle. So the former is illustrated here on the left side. Imagine that you have a system where the lower up temperature limit of the system is the x-axis, and the upper limit is represented here with this dashed line. In a system where you have sensible thermal energy storage, you would need store energy in terms of changing temperature of a material. So with this gradient here is dependent on the specific heat capacity of the material. And during this temperature range, you are able to store this amount of energy. In the latent heat principle, you are storing mostly in solid liquid transition, and that happens at a constant temperature with crystallization and melting. And for the same temperature limit, if you find a material that has a latent or a phase change transition temperature in this range, you're able to store a lot more energy within the same temperature limit, which is often a limiting factor in refrigeration plants where you're operating with quite narrow windows of temperature. And also all these systems has it's a contribution of sensible up to the phase transition temperature and up to the upper temperature limits. That also contributes a certain percentage. I mentioned phase change materials. This slide I would like to talk a little bit more about what these materials are. On the top two rows here, I've indicated kind of where this belong in the overall thermal energy storage materials overview. So you have the sensible materials here, like water, rock, ground, etc. That is the normal thermal energy storage materials. And then we have the latent ones, and we have the thermochemical. I will not touch on the thermochemical. That's a different branch, that is a different technology. But we are focused on latent tests and mostly for solid liquid transitions, because this is the transition where you have fairly low volumetric changes between the solid and the liquid. For water, for instance, it's about 10%, and it's within 10–15% for most phase change materials too. Solid gas is of course then more challenging due to the expansion of the volume. Within this range, we have different groups of materials: organic materials, eutectics, and inorganics. These are the three main groups of PCMs. For cold thermal energy storage, which means subambient, what we define as cold thermal energy storage is materials that is used at ambient temperatures or lower. And in this temperature range, there are mostly paraffin compounds and inorganic mixtures of water and different salts, salt hydrates. The latest years, there's been some development on the commercial market too. I've listed a few of the vendors for PCMs, suppliers of PCMs. We have some German companies, some from the US, some from Great Britain, plus is an Indian company actually, where we have tested a few of their PCMs in the lab, and a few others, a Swedish one. But they have been coming to the market the last 5 to 10 years, also for cold thermal energy storage. So we have certain selection criteria when we are selecting PCMs. We want, of course, the correct phase transition temperature for our applications, and we look for a combination of a high density and a high latent heat capacity, which together makes a compact storage in the sense that we are able to store a lot of thermal energy per cubic meter of storage. We look for material compatibility. For instance, certain metals are not compatible with inorganic salt water mixtures due to corrosion. Paraffins and polymers could be a bad fit, and also, of course, then cost and environmental concerns for the materials. And also, there's more details in this table here for certain other effects such as supercooling and crystallization. In this table, taken from a publication from some years ago, at least, it shows a bit of the temperature range of commercial and non-commercial materials in different phase change temperatures and their respective latent heat capacity. And you see that for, let's say, 0 to -30 and -40, we have quite a few materials. Different ranges. It's alcohols, eutectic salt water mixtures, paraffins, alkans, different substances. But the trend is kind of, we see that as you go down in temperature, you also decrease the latent heat capacity of the material. Yes. So that's what I had on the actual materials. Now we move on to applications of this technology in refrigeration systems. A couple of years ago we wrote let's say a review paper on this topic, where we found that PCMs, as I mentioned, has been becoming commercially available. We have a growing number of suppliers on the market. In the academic world, we have seen that this technology has been investigated for various applications, such as food transport and packaging. That's a passive solution for most senses, that you package the food stuff and medicine, etc., in PCM enhanced packaging to ensure that you have no breach of the cold chain while you're transporting products. We have seen that it's been taken into use in research in commercial refrigeration, supermarket refrigeration systems to quite a large extent, especially for CO2 refrigeration. And also we see air conditioning and industrial refrigeration systems solutions for this. Commonly to most of these, that few of them has been demonstrated in the field, except for air conditioning, where you had during the energy crisis during the 70s and 80s kind of fueled a bit of a sparked interest for thermal energy storage, and ice storage with air conditioning has been demonstrated in Japan, the US, a few of these during the 90s and early 2000s. If we look at the cold chain, I have tried to illustrate the cold chain for food here in this slide, all the way from the Norwegian perspective of the fish, where you have capture production all the way to the consumer here at different steps. We have seen that there's a potential for of the technology of thermal energy storage in industrial refrigeration systems in the processing step. In international transport, there we already have it implemented. We transport all of the fish from the Norwegian fish farms, salmon, on ice, where the cargo is approximately 30% ice and 70% salmon. So we have back calculated based on the export numbers of salmon. We have back calculated there's a capacity to produce ice for equivalent to the size of a power plant, approximately to several megawatts of producing ice on a daily basis throughout the nation. In the retail step, it's also in refrigeration system, as I mentioned, and also in domestic refrigeration, which we have been a topic for a while back, but not very much investigated at this time. What we have been working on at NTNU SINTEF is for the processing step and the retail, so supermarket and industrial refrigeration. Another point I would like to address is that we have two distinct strategies of integrating storage in a refrigeration plant. The first one is to use the refrigerant directly in the heat exchanger, where you are coupling the phase change of the refrigerant on one side with the phase change of the PCM on the other side. That means that so you have a phase change on both sides of the heat exchanger. In the opposite case, you have a secondary refrigerant illustrated here, where you're transporting from the primary refrigerant circuit, so the chiller in this case, to a secondary circuit, which would be a glycol or a water or a brine or similar, to cascade the heat into between the system and the load, which is in the middle. This could be practical in certain cases where you have long transport lengths, etc., but also other things. But thermodynamically, it's more efficient to do it directly, because you avoid cascading the heat or the cold in this case throughout several temperature steps in intermediate loops or circuits. So we have chosen to focus on integrating into the primary refrigerant circuit directly, which is more challenging, but this is where let's say the novelty, all what's been demonstrated before has followed this principle, and it's killing a bit of the round trip efficiency. So these systems are not as efficient as they could have been, and we would have seen much more success in the market in previous years if they have followed the direct integration principle. We identified different ways of integration of thermal energy storage in CO2 supermarket refrigeration. So kind of various enhancements for CO2 refrigeration systems. First one here, the layout one, is indirect subcooling downstream of the gas cooler, where you have a storage. You're cooling it with an evaporator, and then you use the stored cold here to subcool or reduce the gas cooler outlet temperature, which is very important in CO2 refrigeration systems to improve the efficiency of the system. The second here, layout 2, is integrated directly into the cabinets. So you have a storage in between the evaporator of the refrigeration plant and the display cabinet. The third one here is to reduce flash gas from the process. So that could be, it's a bit of following the same principle as layout 1, but you are reducing the flash gas from the high pressure valve in order to improve efficiency. Fourth one is then you are able to use a PCM. You are able to lift the evaporation temperature, because you don't need to do it at the empty evaporation temperature, but you could do it at an elevated pressure upstream the receiver. So this will be an enhancement of the same principle as this, but at a better energy efficiency. Finally, there's also used the same principle as layout 1, but you're using the cold energy in order to subcool the refrigerant before throttling to the before feeding it to the different cabinets, so the empty cabinets or the LT cabinets in the system. So all of these are kind of energy efficiency enhancement strategies that we identified in the literature. We have at SINTEF, we had a project called PCM-F and PCM Store, where we it's currently ongoing also, investigating different PCM technologies for supermarket and also industrial refrigeration systems. Here is an example from the lab where we integrated into display cabinets, which would be layout 2 here in the system, where you use CO2 to in a coil inside a box. Looks like this. The air flows on the inside. This is the back wall of the display cabinets in the supermarket. We use this space that is currently unused. It's just air flowing here, and we put up a PCM CO2 heat exchanger in here. So we freeze water inside here during the off-peak hours, and then we turn off the refrigeration system, and we circulate air with the fans that are located on the bottom here, or the back wall, to circulate inside here to get the cold cooling effect that we need. So we're able to switch off the system during peak. Did some experimental investigation of this concept. You see some of the results here. This is the reference. This is the temperature of the PCM, which is the blue one here, and the orange one is the equivalent temperature at the same spot, but without the heat exchanger. And we have a pull down load here, and then after this point, it's I think here it's been the system is shut off. The refrigeration plant is shut off. And then you see the temperature of the same spot increases quite fast in the case without the PCM storage there, but it has a delayed increase in the using the active PCM storage evaporator. If we look at the air temperature, we see that they follow quite closely the first hour, and then you get, after you get, let's say, a temperature difference from between the air and the water that's frozen, or the ice, of about 10 Kelvin, then you start to get an effect on this. So you're able to, you need a certain temperature difference to have the driving force for heat transfer. So the air temperature is then, we're not able to keep the temperature down, but it's not increasing as much as it does without the storage. But it's clear here that this temperature is too high to be acceptable anyhow. So we need to enhance the heat exchanger in order to get more surface area and pull down the temperature. So there's some room for efficiency improvement here for this kind of system, but the principle would be the same. So supermarket refrigeration is one of the cases that's very interesting for cold thermal energy storage. The other one, which is, I think it's even more interesting, would be industrial refrigeration systems, where you have very high peaks and very high loads. This picture on the top here is a poultry processing plant that it processes and freezes, slaughterhouse. And processes and freezes around 30% of all the poultry in Norway. It's half an hour drive south of Trondheim, where we work at the university, NTNU, and at SINTEF. This has been more or less a case study during the PhD project that I worked on, where this has been realized now. It was commissioned in last year. They have been investigating this kind of cold thermal energy storage concept. They want to implement something like this, but they're waiting for the technology to become mature. So that's what we did research on in my PhD project. So as I said, these are they have really high peak power demands because they're driven as batch processes in freezing tunnels, or it could be also continuously in spiral freezers and so on. But in any case, if there's no production, the refrigeration load during the night is very low. It's just for the keeping the product frozen in the freezing storage. So that's a relatively low load compared to the process load. So the target is anyhow to do peak shaving of the refrigeration load, but the current status is that there is no solutions on the market that is rated for high capacity. That could be a good investment for this kind of plants. So we started in 2016-17 to design and come up with a solution that could allow a direct integration, as I talked about before, to be allowed to do it directly in the refrigeration system without any intermediate loops. And also one of the motivations was that the plant also, they decided to go away from glycol as a heat carrier fluid on the -40 and go directly with CO2. So there was CO2 piped already hundreds of meters around the facility. So we needed something that could accommodate this as well. So it was both from the thermodynamic perspective and also from a practical, it was good to go for this kind of solution. So it's based on, we developed together with a manufacturer in Trondheim, we developed a thermal energy storage unit consisting of this kind of pillow plates. They are stainless steel plates that are welded together in a laser welding machine, and then after that it's inflated, so you form this kind of wavy surface, and that's why it's called the pillow plate. In these kind of plates, the refrigerant flows inside here, and we place it in a container and we fill it up with the PCM, so that the PCM is in between these plates. We are able to change the distance between the plate here to increase the storage capacity and play around with this kind of parameters. We had to construct a experimental test facility with CO2, pumped CO2 circuit in the lab. And here you see the experimental facility, and we are also connected to a centralized refrigeration plant, CO2 refrigeration plant at campus, which is giving us the opportunity to vary the evaporation temperature between, let's say, +5 to -45, -50. So you are able to test a lot of different PCMs in this kind of setup. And we provide the heat input for simulating the refrigeration load in the system with this internal glycol circuit. So the refrigeration plant at the poultry processing location is a CO2 ammonia cascade refrigeration system. A cascade refrigeration system means that there are two circuits that are interconnected in a cascade heat exchanger, so that the bottom cold, or let's say the low temperature portion of the plant is CO2, and it's rejecting heat to the ammonia circuit, which is then on top and we're rejecting to the ambient temperature. So this is the illustration of a simple layout of the CO2 system, which is a -5 circuit and a -40 circuit. -5 for chilling and -40 for deep freezing. What is indicated here in green lines is what is needed to integrate such a storage in the plant. So how it works is that we connect the storage, or let's say it could be also many units in parallel, but in principle it would be the storage on this one, connected to the liquid line, and then throttle it down while we're charging. Throttle, we evaporate CO2 inside here. We throttle down lower than the phase change transition of the PCM. That means that the PCM will then solidify, and the PCM, or the CO2 will then evaporate inside this kind of plates. We use one spare compressor, which is not used during the night. Could be also several of them. We isolate them from the rest, and we are able to reject the heat to the cascade heat refrigeration system. This stop motion here shows how the PCM is solidifying on the surface, the cold surface, where CO2 is evaporating on the inside. So it grows quite fast in the beginning, but also then grows all the way together. So when it's fully grown together, this solid PCM is what we call fully charged, or the system is charged. And the time it takes from fully liquid to fully solid is the charging time. So that's how it works when we store the thermal energy during the night or the off-peak hours. Some example results here that we got from the system. We see in this upper graph here, we see the evaporation temperature of the mean CO2 evaporation temperature during the charging process, and the resulting charging time for two different configurations. One configuration with 30 millimeter space between the plates, and one with 15 millimeter distance between the plates, effectively doubling the capacity in terms of storage capacity. In this case, we use a PCM that solidifies at -9 to -10. So the solidification temperature is indicated on this axis here, more or less. So we see that the charging time reduces quite drastically, while we reduce the evaporation temperature of the CO2, which is natural because you have a larger temperature difference to drive the heat transfer. And as we solidify more and more, it's mainly conduction driven on the PCM side that is limiting the heat transfer. So we see that for both configurations, it seems to be that we have a good reduction up to about 5 Kelvin difference, and then you start to gradually decrease the benefit. We know that as we reduce the evaporation temperature, we also reduce the efficiency of the CO2 system. So there's a, let's say, a compromise in terms of energy costs and charging time. For the bottom graph here shows the pressure loss through the unit. With a fixed mass flow rate, we see that we have actually an increase in the pressure loss across the refrigerant across the unit as we reduce the temperature of the CO2. This is due to that we have higher heat transfer, which means more CO2 is evaporated as we go down in temperature, and then the higher vapor fraction increases the velocity, and we have a higher pressure loss. So that's the cause of this. But we see in all cases that the pressure loss is quite moderate in the sense that we have in worst case up to 0.55 bars for this kind of unit. So when we have stored the energy, we have the unit is fully charged. Then we connect it. We use some valves. We have a return from the plant to the machine room with a vapor liquid mixture. We send that through the vapor liquid mixture through the unit. It's a pump circulation system. I should say that it's a pump circulation system. So it means it's working in overfeed mode, which means that the return is always, it's not 100% vapor, it's always liquid vapor. That's how these kind of plants are operated. So then we have this mixture entering the unit, and it's returning at -5 approximately. It means that we have higher temperature than the phase transition temperature, and the CO2 is condensing inside the plates. The vapor is condensing, while the PCM is melting while it's absorbing the heat from the CO2. So it's the melting from the inside out, which means that we have melting, as we can see here. It's not uniform because it's actually some natural convection inside the PCM while we have a temperature difference. So this effect is it's not been quantified, but we predict that this could be very important. And we have some results here, and we see that we have while we change the condensation temperature of the CO2, we see that we had higher discharge rates, which means that it's melting faster, and we have a shorter cycle. This is for one pitch. Using this, in this case, we use water as the PCM. We also did the same test for the low temperature PCM at -10. And as for the evaporation processes, the condensation temperature is the most important because it's the temperature difference that is driving the heat transfer between the CO2 and the PCM. This has been for the -5 system. If we're going to go target the very low temperature processes, -30, where many of the refrigeration systems are operating for tunnel freezers, blast freezers, etc. They have very high peaks during the initial phase because they are batch driven. This is illustrated here in a tunnel freezer where you have evaporators here, some fans, and you're circulating across some trays where the product is frozen. So we have a typical transient curve for the refrigeration load. If we look at the materials available in this temperature range, we see that we have it's a challenge to find something that will be good. We have tested quite a few of these organic salts or these inorganic salts, but they have certain problems with incongruent melting, low stability, etc. So we see that also for this, it's more or less the same salt with different concentrations, gives you different melting temperatures. So there's few available. This is just from 2 manufacturers that we have found that supply temperatures in this kind of in this range. So what have we been working with recently is using CO2 as a storage medium in the liquid solid transition. The reasons for doing this is that we know that CO2 it's abundant, it's safe for the environment, and we have in both industry and from the research perspective, we have a very long experience in handling this kind of fluids. It's challenging because we need to investigate whether this works or not to keep cycling between the solid and liquid line of CO2, and we have to keep it above the triple point to avoid vapor formation. But it has very interesting properties in terms of storage. High density and also high latent heat capacity, or relatively high latent heat capacity. A few examples from before. We have Professor Armin Hafner has been working with this, so suggesting this on a theoretical level. We're using in CO2 ammonia cascade refrigeration system. It's also been taken up by a master student that he had a couple of years ago for a freezing vessel. But for now, it's been only theoretical concepts. It's a challenge because we have to pressurize the system, which could increase costs. And it's not sure that the principle of operation, so it needs to be proved experimentally. And also the challenge of vapor formation that I mentioned before. So we have planned setups to prove the operation. And we're trying to do different setups with, for instance, a tube-in-tube for visualization. And also a pillow plate setup would be interesting to test. So we foresee some kind of, this is on a concept stage where you have kind of a rolled piece of pillow plate inside a cylindrical tank to store the CO2 using a low temperature fluid for charging, for instance, ethane, a refrigeration cycle. Future perspectives, I'm closing to the end here now. Challenge that we have discovered with our work in this is that we are limited in the heat transfer in terms of the low thermal conductivity. There are enhancement techniques that could be applied to improve this, or we can increase the heat transfer area of the heat exchangers, which translates to a higher cost. The selection of PCM is a challenge because price and availability is kind of limited at the moment, especially for low temperature. But we could have certain measures to integrate the storage into a location of the system where you could use a higher temperature. And of course, if you are able to use water and ice as a storage medium, that's the best option because it's safe and cheap and we have very good properties. So far, it's been tailor-made solutions in the field. We need demonstration sites to increase the confidence in end users of the technology. And we need the cost down of mass production in order to be cost competitive at the current time. And then there's the big remaining challenge of control: when to charge, when to discharge. Should it be integrated with predictive control, pricing models? It could be a lot of input and interesting collaboration with researchers from control departments that we have ongoing now in our group. So a quick summary at the end. Thermal energy storage is really a key component for the future energy system, where the energy mix has a high share of renewables. It can provide very much needed flexibility and reduce the strain on the power grid and avoid expensive infrastructure investments in the future. Coal thermal energy storage has been investigated quite heavily in the academic world for the past decades, especially focusing on food packaging and transport, supermarket refrigeration, especially for CO2, and in industrial refrigeration systems. We have seen that there are few installations in the field, but this will be the very next step to move this technology up the TRL scale. And finally, a point on using CO2 as a solid liquid storage material has, we believe, a high potential for low temperature CTS, especially for food processing and freezing processes. So here are some references from the talk. It's been mentioned. It's in the slides, and the full references are here. And I thank you for the attention, and I'm happy to answer any questions for the remaining minutes.
Participant can just raise their hand so we can unmute for the question answer, or they can even write question answer then in chat box. Yes, sir. Yes, sir.
Yeah, I have got a small clarification. In one of the slides, you told that latent heat decreases with the decrease in temperature, whereas in the later slide, when the E20, E60, E50 and all, their latent heat is same, regardless of the storage temperature.
Yeah, it's the, let's say, the general trend is that the lower you go in temperature, the less you get in latent heat. But in certain cases, if you're increasing the share of the for the same salt water mixture, it could be that you actually increase in the small. If you look at the small, if you're looking at the certain salt, so if you increase the fraction of one salt that has a higher latent heat, then you could actually improve in that case. But general, if you're looking at from, let's say, from 0 degrees down to -60, you have a decrease. But for one salt, it could be that you, depending on a bit on the specific concentration.
Mm-hmm. And the other one is, can you explain that a PCM material embedded in the like a pillow? You talked something like, I'm not able to grasp how you did this. Plate heat exchangers with the embedded PCM.
Mm-hmm. And it's actually easier to show the slide. Okay, let's take this one.
Yeah, previous one that where you got, that's and
yes.
previous one also where you got pillow or that the plate you have embedded this this one, this one, yes.
Yes. So the plate heat exchanger is placed inside this container. And this side here, we have the manifold. There's one tube on each end of this where we connect the CO2. It's a simple manifold. It's really just a tube and some connection with it's been changed to braided hose here, distributing the refrigerant inside the various plates. So then the CO2 flows inside these very narrow channels, and everything is just immersed into the PCM. So yeah, that's how it works, and it's flowing from one end to the other, so it's evaporating as you go across here. It's not vertical, but it's horizontal in here. We have also tried vertical, which will be probably the next design, where we have a implementation for an office building, where we use a vertical.
Where is the PCM material now? Where is the PCM material?
So in here it's empty, but it's filled in this container. So everything in here is immersed as it is shown here. So it will be, we are filling for the test that we did with water and ice. We just filled everything up here, and the same for the PCM. We bought about 500 kilos of the PCM to fully submerge this kind of heat exchanger into the liquid. So that's the advantage of when you're doing cold thermal energy storage, that you are able to, it's all of these PCMs are liquid at room temperature. That means you can fill it in like water. So it's like let's say an oily substance that you fill in a liquid state, and then it solidifies only when you freeze it or when you cool it down with the CO2.
Okay.
So that's how that works.
Okay, thank you. It was a wonderful lecture, Hakon. Thank you very much for your elaborate slides and information on this topic. Thank you very much. Thank you.
Thank you.
I enjoyed it. Thank you.
If there's no other question, we'll thanks Peter for this an excellent talk on thermal energy storage for the supermarket and industrial application.
One question from
Yeah, it's
Kamal Jyoti.
yeah,
Dr. Kamal Jyoti.
Dr. Tamal Jyoti Tatuldar. Yeah, you can speak.
Dr. Kabaljoti, you are muted.
Hello. Hello.
Yes, sir.
Yes.
For using this carbon dioxide as PCM, so basically we are storing it in solid form or liquid form.
Storing in solid form. So we are trying to store it in dry ice and then transition it between liquid and solid as we do for PCMs or like let's say conventional PCMs. We're trying to do that. We know that there has been dry ice is used in, for instance, been used for the COVID vaccine that needed -70. They use dry ice for keeping the vaccines cold, but then it just evaporate. It goes from it's at the room temperature or it's at the atmospheric pressure. That means that the dry ice will sublimate directly to vapor and just be released to the atmosphere. But we want to create a system where you can cycle it as a normal PCM from solid to liquid and then store in the solid form as is in crystalline dry ice.
But the energy consumption for storing this carbon dioxide in liquid or solid will be more, no? We have to cool it down.
Yeah, it's you need an additional cycle. So it's a question of whether is it worthwhile to go for storing it in let's say the CO2 in dry ice form, or we should go for a PCM solution and then maybe integrate it in a different spot of the system. So you use a compressor to lift parts of the way so you could store at a bit higher temperature. You will not be able to reduce the compressor capacity completely when it's peak hours, but it could be worthwhile to maybe store at -20 or -10 depending on the system configuration. But we want to investigate the possibility to, at least on the lab scale, to check if how much energy is needed. Is it stable? Is it can it be cycled in like say conventional way as PCMs?
Thank you.
We can get one more question from this Santar Lal.
Shankar Lal, sir, you can go on. You can unmute yourself and talk.
Hello. Yes. Hello, Mr. Santarla. Is it audible? You will read. Okay, I think he has lowered the hand. So we'll just thank Dr. Hatton and we'll move up the next presentation of this session. So next presentation is by Dr. Kristina on the industrial ammonia refrigeration system and potential for cold thermal energy storage. Unfortunately, she is not with us, so we'll play the recorded video by her. And I'll just introduce the speaker that Dr. Kristina is a senior research scientist at the Research Institute SINTEF OC in Trondheim, Norway, working at the Department of Fisheries and New Biomarine Industry. She received her PhD degree in Energy and Process Engineering from NTNU Norway. Her research addresses mainly focusing technology and system for the food industry, especially related to refrigeration and food cold chain. Examples of research activities are increasing energy efficiency, reducing global greenhouse gases emission, increasing utilization of natural refrigerant, improving product quality, and reducing food waste. So I'll request Vaisat can play her video.
Hi, everybody, and thank you for inviting me to this event.
Pradeep, is it audible, right?
Yes, it's
Okay.
audible. We continue.
It's audible. Carry on.
Okay.
My name is Kristina Widell, and I work at SINTEF OC in Trondheim, Norway. Today, I'm going to talk about industrial ammonia refrigeration systems and potential for cold thermal energy storage. These are the contents of my presentation. I will start to talk about a little bit about the background, UN Sustainable Development Goals, food value chain, and greenhouse gas emissions. Second part will be about industrial ammonia refrigeration systems. I give you an overview and also some examples from fish processing industry and fishing vessels. The focus is on applications of ammonia refrigeration systems. Third part is about reducing carbon emissions. Talk a little bit about natural refrigerants, but I know many others are also talking about that during these events. I will talk about heat recovery and thermal integration, and also a little bit more about improving operation in general. And at the end, I will talk a little bit more about cold thermal energy storage, and some summary and conclusions at the end. I guess you all know about the UN Sustainable Development Goals, and nowadays it's the background for much of our work. I will here tell you a little bit about a report and a web page, which can be interesting for you as well. This report came this year, and it's an independent and quantitative report on the progress we have so far related to UN Sustainable Development Goals. If you go into the web page, you can also find an interactive map which gives the status for each country and also each goal. So this map here summarizes the progress for all the goals. The darker the color, the better the progress towards the goal. So here we can see it could look quite okay for the western part of Europe and not that good for India. However, we should not look only at all the goals together. That doesn't tell us very much, but go into each goal separately. So if we go into, for example, this goal number 12, responsible consumption and production, you see the color coding here on the top right. So red means major challenges remain. Northwestern part of Europe has quite a lot of red, and India is here green. And we can also have a look at other of the goals. There's number 13, which is climate action, 14, life below water, and 15, life on land. And we see quite a lot of red here, which means then the major challenges remain. And that's also what we are working with. We are looking for solutions, and we know that we can and we have to solve this with research and innovation together. And what is also interesting is that all these goals here are related to the food value chain. So what is the food value chain? Well, we call it the food cold chain when refrigeration is included in some part of the food value chain. The food value chain is often what you see here, is production, processing, retailers, and consumers. If we go into more detail, it can look like this. This is an example. And we have then production, harvest, slaughter, transport, some processing, could have further transport and also storage and repacking before it comes to retail and again transport to the consumers. And examples of refrigeration within the food value chain is, for example, freezing, chilling, super chilling, but drying can also be part of this. Especially when we talk about SDG 13, the climate action, we talk about greenhouse gas emissions. Data show that 1/3 of total greenhouse gas emissions are related to food systems. And the graph here shows global emissions in 2019. It shows how it's divided between the different parts of the food value chain. 13% representing the farm gate, and 11% from the post-farm gate, and 7% because of land use change. We also know that 60% of food is refrigerated, but refrigeration requires energy, which gives emissions. However, we also know that 20% of food produced is wasted in the EU, and even more, 1/3 of food produced is wasted in the world. So we need to keep our heads in the products cold and remember this. Keep product quality high with less use of resources and low emissions. Now we will look into more details on where the emissions come from. These graphs shows total emissions per stage of the cold chain. India is on the left and Europe on the right. Green is energy consumption, yellow is refrigerant leakage, and orange fuel diesel consumption. And everything is in million tons CO2 equivalents. Please remember that this tool only looks at emissions from the cold chain, so it doesn't look into emissions from losses. With emissions related to losses included, these graphs would look quite differently, especially where there is no cold chain establishment, which is the case in many places in India. In Europe, the largest emissions are from the transport and the retail stages, and these numbers are from the FAO, an emission tool that IIR has. So, how can emissions be reduced from the food cold chain? I will come back to this later as well in more details, but this is a short summary. So, reducing emissions in the systems or in the equipment can be done by adopting natural refrigerants. You can reduce energy on demand, and of course also increase system efficiency through, for example, thermal integration, thermal energy storage, etc. We can also reduce food loss and waste by raising the consumer awareness, more and more efficient refrigeration of food, and also better control of food value chains. Now I'm going to follow up the previous slide with a little more details, and here are some examples of solutions to reduce greenhouse gas emissions in food cold chain, and also where they can be applicable in the cold chain. We have, for example, natural refrigerants, which can be applicable in the whole food value chain. We have also high temperature heat pumps, which is mainly for the processing stage. We have heat recovery and thermal integration, thermal energy storage, sustainable packaging, integration of renewables, super chilling, monitoring of energy, food waste, etc., and improving operation. There are different methods to work with these topics, and those include awareness, raising awareness, also again along the whole food value chain. We have financial mechanisms, technological development and innovations, and policies and regulations. Now I come to the second part of my presentation. I will focus on what we have in Norway, especially within the fish processing industry, We had systems on board fishing vessels and in land processing plants. And there are many similar systems in India, but also large differences in applications, and I guess especially on board fishing vessels. R22 has been used before as a refrigerant, but as you all know, it has an ODP and also global warming potential. And because of that, it's forbidden to refill in Norway after 2016. So there has been a clear change in the use of R22 and also other synthetic refrigerants. And here are some data for fishing vessels. In 1993, 91% of the refrigeration systems on board had R22. In 2007, the same number was 82%. And today, all new systems have mainly ammonia as a refrigerant, and also a few has CO2. Although my presentation is mainly about fish processing, we know that natural refrigerants are used in other sectors as well. This graph shows which refrigerants are used in Norwegian vegetable storages, a survey that was done recently. It covers about 37% of total vegetable storage volume, and the others that didn't reply to the survey. Blue is share of systems and orange is share of total storage volume. So almost half of the storages were more than 30 years old, which probably explains that we still have R22 here. Unfortunately, we still have synthetic refrigerants, but there is also systems with natural refrigerants like hydrocarbons, CO2, and a few with ammonia. Many of the storages also have no refrigeration system at all, only natural cooling. And although we have no measured numbers of food losses for those, it is assumed to be 15 to 30% depending on the type of vegetable. So better control and more refrigeration will likely reduce that number. Now I come to some examples of applications of industrial ammonia refrigeration systems, starting with chilling of pelagic fish on board fishing vessels. Some examples of pelagic fish is herring and mackerel. And these photos show the inside of the large RSV tanks. So when the boat travels to the fishing ground, they fill the tank with water and chill it, and they have large ammonia systems on board. Fish is then filled into the tanks and the water is circulated to keep the fish cold until it's pumped to land. This is an example of an RSV system. Blue lines represent the seawater and yellow lines the ammonia. They have here two parallel systems to be sure that they always have enough cooling capacity. The condensers are cooled with seawater. The RSV circulated into in this case, the 9 different tanks, depending on how much fish they have on board. Here is another example. Whitefish, like cod, saithe, haddock, can be frozen on board in plate freezers, which you can see here in the photos. Ammonia is commonly used as refrigerant, but CO2 systems are also now available. Lower evaporation temperatures, which you can have them with CO2, results in faster freezing, which is good for keeping the product quality high. So not only the time in the freezer is shorter, but also more fish can be frozen at the same time. Next example is freezing on land of pelagic fish. Example here is with the mackerel, and it's commonly done in freezing tunnels where the fish is packed in boxes and put on shelves, as you see here. And you have the evaporators on the right hand side of this photo. One tunnel can include 100 tons of fish, and it's often freezes during a period of 20 hours, so for quite a long time. After that, the boxes are transported into the freezing storage, where the temperature is controlled by much smaller evaporators. So it's really important that the fish is fully frozen inside the freezing tunnels before it's moving into the storage, because there the freezing is much slower. This shows an example of a PNID for a central ammonia system serving freezing tunnels, freezing storage, and room cooling, which are marked in yellow here. It has many compressors of different sizes marked with K and a number here, allowing for optimal operation. So frequency converters are also common, at least on one or two of the compressors. The condensers are chilled with seawater, which makes the operation efficient, especially if they are cleaned regularly. Here is an example of fillet freezing in impingement freezer. In this case, mackerel is caught during a few months of the year and frozen in tunnels, as shown previously, is most of the fish. However, some of the mackerel is filleted and frozen in impingement freezers instead. And that type of freezing is much faster. We're talking about less than an hour compared with 20 hours. And then the products are also ready for the consumers to prepare. Much of the tunnel frozen fish is exported as it is, but some of it is thawed and processed outside of the season as well. And the blocks of fish you can see here is thawed in brine and filleted afterwards, and which results in a fish temperature of below minus 2.5 degrees. And this keeps the quality high and allows also all year production. Salmon industry is quite different from the fishing industry. Salmon is farmed, production is more even all year round. And we can see here when the salmon is ready for slaughtering, it's brought into holding cages, and after that it's pumped into the processing plant where it's stunned and killed, put into chilling and bleeding tanks. And they can look like this. So the chilling tanks here are filled with refrigerated seawater, and they are in this tank for about 1.5 hours or a little bit longer. This is another photo of it, how it looks like. And as you see, there are quite a lot of blood in the water afterwards. When they have been chilled here and bled, they go to further processing. It could be filleting or chilling or freezing. One interesting aspect with this is that we first chill water, which then chill the fish. And the cold water is often discarded afterwards. So there is potential for recovery of the cold. At least it should be evaluated. The cold could be recovered with, for example, heat exchangers or water treatment, filtration, etc. Based on specific capacity of fish and water and temperature differences, heat loads were calculated for cooling of fish with water. And this table shows the results for different temperature differences. meaning the difference between end temperature after the process and temperature when the cooling starts. It shows calculated heat load from fish compared with total heat load. That means fish and water together. So that's why we have the percentage. It shows that low temperature in fish, a small delta T, and high temperature water, a large delta T, for that case only a very small part, 11% of the chilling capacity actually goes to chilling of fish. Now I'm at the third part of my presentation, which is reducing carbon emissions. And I come back to this table and I will talk a little bit more in detail about these 4 topics, which is natural refrigerants, heat recovery and thermal integration, improve operation, and thermal energy storage at the end. The first topic is natural refrigerants, which I guess you have already had many presentations about, so I will not explain why they should be applied. For refrigeration on board fishing vessels, there are a few different refrigeration alternatives. Often it depends on the type of fish or seafood, and it is the same for other food sectors. There are many good possibilities and solutions with natural refrigerants. Development and innovation also make this interesting. There are, for example, development in capacity and size of CO2 compressors, which makes them more interesting for industrial processing plants. So if you are interested in this, you can find reports and papers and presentations in the webpage for the Coolfish project. Heat can be recovered from the refrigeration system and used in the processing plant. So this is an example which I have shown before with the central ammonia system. It has heat recovery from the superheat heat exchanger and from oil cooling of the compressors. The surplus heat from the refrigeration system can be used for several purposes. For example, ventilation, floor heating, domestic hot water production, and heated water for cleaning of the plant. Some of the heat can also be used for melting of ice outside. Water for cleaning of processing equipment is further heated to 75 degrees by an electrical boiler, and the boiler also heats water when there is not enough surplus heat, for example at periods of low production. So this graph shows the power consumption of the refrigeration system and the electrical boiler. So we see here that whenever the refrigeration load peaks, load on the boiler is low, and also vice versa. This is another example. This is from a meat abattoir. Steam is often used in industrial food production plants, both for processing and for hot water production. Hot water is further used for tap water and for cleaning. Some of the external energy used to heat the water could be substituted with surplus heat from the compressors and the condensers in the plant's refrigeration system, which is what we see here. Tap water comes in at 10 degrees and is heated with surplus heat from compressors. Some of the 40 degrees water goes directly to hand washing station, and some of it is further heated by an ammonia heat pump that upgrades the condenser heat. So the use of energy for hot water production in this abattoir was analyzed in a paper in 2013. The monthly energy consumption was recorded, and the results showed a significant reduction in external energy requirement for hot water production. External energy use as part of total energy to heat the water was reduced from 55% to 13% because of the extra heat recovery installations. And the carbon footprint was also calculated, and with the new system it led to a 60% reduction. It is seldom that an industrial refrigeration system is totally optimal, so there is always room for improving operation. And good operation of compressors and frequency converters has been mentioned before. It is important to avoid inefficient part load operation. Good control of fans in freezing tunnels is also important. Not only do they use electricity, they also add heat to the tunnel, which must be removed by the refrigeration systems. Cold recovery has also been mentioned. At least it should be evaluated. Energy efficient operation of the entire processing plant. Often it is best if all personnel working in the processing plant is aware of this, and it makes it easier to follow up. An example of that is to turn off equipment not in use, or as you see in this graph, measurements of specific energy consumption for different parts of the processing plant. That can also make it easier to improve the operation. Another big topic is to utilize all resources better, where the rest raw materials should be looked at as resources and not waste. And they can be used, for example, for high-value ingredients to high-value proteins and fatty acids. Now I will talk about cold thermal energy storage, starting with land processing plants. First part, I will begin with presenting results from a paper that we had at the Gustav Lorentzen conference this year. The main objective of this paper was to describe and analyze data from a Norwegian fish processing plant which freezes mackerel and herring in hourblast freezing tunnels. And suggestions to implement cold thermal energy storage was also given. The refrigeration system is the same as I have presented before. The total cooling capacity is 4 megawatts, but the entire unit is only required during days with high production. And the ammonia charge is 30 tons, and if you want to read the paper, I can share it with you as well. This graph shows average monthly production volume at the fish processing plant for the years 2017 to 2021. So the numbers are relative, which means that they are normalized against the month with highest production volume within the period. So which is not then shown in the graph. Anyway, it shows that the production follows a seasonal cycle and is linked to seasonal availability of fish. So we see here there is a lot of production in January and February, and mainly in the autumn, peaking in October. This graph shows total daily energy demand at the plant for 2021, and it shows that the variation throughout the year is, as expected, heavily linked to the seasonal production cycle. So during the periods January to February and September to November, daily energy usage is measured at levels almost tenfold compared to the non-production period March to May. The blue line is the monthly peak power, and it is the hour of each month with highest measured power demand. So during production periods, the peak power is measured to be around 5.5 megawatts compared to less than 1 megawatt for non-production periods. The figure reveals that even within periods of production, there is a significant day-to-day variation in energy usage. For example, January consists of daily levels at both above 100 megawatt hours and as low as 10 megawatt hours. Although some of the low demand days seems to be set during weekends, there is no definite pattern, as production seems to take place whenever raw material is available and must be processed. An important condition for a successful implementation of the cold thermal energy storage system is knowledge of the production cycle and being able to predict days of higher cooling demands. However, the knowledge of variation in energy demand in different time periods indicates a potential for peak shaving by CTES implementation. The processing plant has reported high energy costs as well as high associated costs for peak power demands. Stopping the production at certain periods to cut the power peaks is not an option, since it could negatively affect the quality of the products. And another point is that the fishing vessels could be waiting to unload their fish, which must be done continuously and efficiently. A solution to the varying refrigeration load and high peak power cost can be to install a cold thermal energy storage system with phase change material, PCM, as the storage medium. CTES systems with PCM utilize the latent heat of the material to store the thermal energy and have gained considerable interest in the recent years due to high compactness. It has also been shown that implementing a CTES system with PCM into refrigeration systems can lead to reduced part load operation and reduced energy demand. Recent research has shown that CTES combining PCM with a pillow plate heat exchanger, as you can see here, an example of, is especially well suited for integration with pressurized refrigerants at large scale. When analyzing the log data from the processing plant, it is clear that the load varies both on a seasonal basis and from day to day. A CTES system has not been implemented yet, but the potential has been evaluated. For CTES systems with PCM, the most relevant strategy would be to cover the daily load variations, which for example can enable using low electricity prices during nights. The illustrations show that the most suitable location of a CTES system in the processing plant would be connected in parallel to the freezing tunnel, which is then the LT evaporators here. The CTES unit would be charged by supplying and throttling liquid refrigerant from the liquid separator, the receiver. The peak shaving can then be obtained by forcing the liquid vapor mixture from the freezing tunnels through the CTES unit to condense the vapor and thereby unloading the compressors in the plant. The phase change temperature of the PCM of the considered CTES system must be at least 10 K below the evaporation temperature of the tunnel freezers for efficient heat transfer. There are not many reliable commercial PCMs available with phase change temperature below -40 degrees, but development is ongoing. An attractive option in this temperature region is using solid CO2, dry ice, as a storage material, shown in the right figure. The left system requires a reduction of evaporator temperature during recharging, which leads to higher energy use, and if dry ice is used, additional compressor for recharging is required. However, the advantages of using a CTES system are increased flexibility for the use of power, reducing power peaks, and providing backup cooling in case of compressor malfunction. Last part of my presentation is about thermal energy storage on board fishing vessels. This is from a paper also presented at the Gustav Lorentzen conference this year. A report with more details is also available. So this was a theoretical analysis, so the system I will show has not been built within the project. Reducing fuel consumption is one of the most critical steps the fishery sector could make to reduce its climate footprint. The refrigeration systems on board fishing vessels use electricity produced in the engine which is using fossil fuels, but the alternative limiting the use of the refrigeration system is not possible, since refrigeration of the fish is essential to preserve the product quality. The cooling demand will vary from boat to boat and trip to trip. Operating the system according to the design parameters is difficult due to the unpredictable nature of fishing. So weather, catch size, and cooling demand are some of the factors that can result in inefficient use of the refrigeration system. So these factors and the refrigeration system design can make the system run on part load, which results in unnecessary greenhouse gas emissions. So one possible solution to counteract the part load operation is integrating or utilizing cold thermal energy storage. There are already several ways to store cold thermal energy on fishing vessels, and I will describe a few of them, starting with temperatures above -2 degrees. The easiest and probably among the most common is to bring ice from land, and the ice is then produced from pure water. The fish is put on ice and kept cold. And the smaller the ice particles, the better is the heat transfer, because there is a better connection between fish and ice. Another way to utilize ice as CITES is to use ice in an ice maker on board. So this configuration could be used to distribute the peak refrigeration loads by making ice during low periods and supplement with ice when the chilling tank loads are high. This system requires some extra components, mainly a separate ice maker, crusher, and storage for the ice before use, which is illustrated in this figure. Maybe not so often thought of as CITES, but RSV is a sensible thermal energy storage and a widespread cooling method in use today. I have talked about this earlier also in the presentation. This graph shows temperatures of fish and seawater. The blue line is seawater temperature and orange line is fish temperature. In this first part of the graph, the seawater is cooled down to a set point. In the second part, here the fish is put into the chilling tank and the temperature of the fish and water equalizes. And in the last part of the graph, the mixture is chilled down to the desired end temperature. The time it takes for each of the steps depends on the start temperatures and the ratio between fish and water. Ice slurry is a mixture of liquid and ice. The slurry could be pure water or a binary solution which gives a low freezing point. Sodium chloride, common salt, is the most relevant for direct contact with fish. There is a risk of salt uptake in the fish, and the slurry contains salt, and this must of course be considered before using it. However, some white fish in Norway is used for clipfish, which is then salted anyway in further processing. In the ice slurry, there are many microscopic spherical ice crystals mixed with a liquid, which means that the slurry appears liquid. This property makes it a good working fluid for cooling applications. Due to the latent heat of the ice slurry stores more cold than RSV for the same volume. And it could be handled as a liquid, which means pumped and moved around without clogging the pipes. Unless the ice slurry is used at the same rate as produced, the system requires a storage tank that stores the ice slurry. This tank is the CITES in the system. In this figure, it is illustrated that the storage tank has been divided into a poor and a rich layer of ice slurry, You see here different colors. So the system requires either a separate mixing device, as shown here, or a stir in the storage tank to ensure a proper mixing ratio of ice and water in the ice slurry. So the easiest use of ice slurry is to bring it from land, and that system would consist of only two parts, a storage tank and a mixing device. A significant advantage with a system like that compared to ice brought from land is the reduced manual handling of the ice slurry. The mixing device could pump the ice slurry to different tanks and easily distribute it evenly. This system is mostly relevant for smaller fishing vessels without an existing refrigeration system. Again, this paper was a theoretical analysis, so the systems shown have not been built within the project. However, we are looking into the possibilities of exploring ice slurry systems more. So the advantages with these systems are fast chilling and compact systems. However, there are some barriers also. Education and information can be lacking. Costs for those systems could be too high, and sizes of the systems could be too small. Although there are several solutions on the market, I also believe there is a potential for development of technology and solutions. It is more common in Iceland than in Norway, and more common in aquaculture than in fisheries, and it seems like good stories is important for increasing the use of the technology. A few other technologies, especially for temperatures below -2, were also described in this report, and these were then also theoretically evaluated solutions. A PCM unit for chilling is shown here, and this system was described by Said in a paper from last year. It needs further development to be applicable, but which means finding the right PCMs and temperatures, etc. Another solution that has been described in the report is PCM embedded in the chilling tank. If it is relevant or not depends on the type of tanks and availability of relevant PCM. In another paper by Said, the possibilities of utilizing the coal of liquid natural gas in new vessels have been evaluated. The capacity of this is not very large and it requires some additional components, but it may be evaluated further, especially for the maintenance cooling on the way back. In a paper by Verpe from 2019, results from a numerical and experimental study of freezing time for fish in plate freezers on board fishing vessels were presented. The system is a two-stage seawater-cooled flooded evaporator CO2 freezer system. So the figure to the right is showing the charging and discharging process of the CETAs. The temperature range of the evaporator was varied from -30 to -50 degrees. I am now at the summary and conclusions, and I will remind you about working for the Sustainable Development Goals and to reduce greenhouse gas emissions. This is the overview you have seen before of different measures to reduce emissions. There are some potential in using cold thermal energy storage in the industrial food processing systems, but it needs further development and evaluation. Always remember to keep product quality high with less use of resources and low emissions. Thank you very much for your attention. If you have some questions, please send me an email. And here are links to some of our relevant projects. Thank you.
So participants can write their question in the chat box, or we can directly they can directly mail to this ma'am.
Okay, Pradeep, then probably we'll have a 10 minutes break because
Yeah.
5:50 now.
Yeah, so we'll have 10 minutes bio breath, and we'll get assemble by 5:50, if 5:55, or maybe start from 6. So we'll try to assemble in 10 minutes.
Yeah, Vaishak can pass the video.
Yeah.
Pradeep, you can start, Pradeep.
Hello, welcome back. The studio session. So we have the last presentation by Professor Sheshadri Satyanarayanan from IIT Madras. He will be presenting on the CO2 heat pump and chillers. So Professor Satyanarayanan is an associate professor at Department of Applied Mathematics, Indian Institute of Science Madras, Indian Institute of Science Technology, Indian Institute of Technology Madras. After completing his MS and PhD from Texas A&M University, US, Professor Satya worked as a postdoctoral research associate at Reuters University in the field of bioaerosols. Later on, he joined General Electric's Global Research Center in Bangalore, India, where he worked in the thermal sciences lab. In GE, he was involved with the thermodynamics and performance analysis of biomass and solar plant, waste heat recovery systems, atomization, methane and heat transfer projects. Dr. Satya then became the R&D leader in Forbes Marshall Tech Center, Chennai. He was actively involved in guiding product and technology development activity for Forbes Marshall in the area of combustion, steam instrumentation, and control systems. Currently, he is the principal investigator in the Energy and Emission Laboratory in the faculty advisor in the Nirman Pre-Incubator Center at IIT Madras. So I'll request Professor Satyanarayanan to continue his talk. Thank you, sir.
Thank you very much, Dr. Pradeep. Very good evening to one and all. Sorry, I got a little delayed. I would be talking about very briefly on our effort to develop a CO2 heat pump chiller combination for Akshaya Patra's kitchen. So this is a project supported generously by SINTEF and NTNU. I will express my sincere appreciation and thank to Professor Armin Hafner for enabling this project, and also to many of the partners who have contributed by way of equipment donation and also expertise to help us realize the system. There is a system in progress. So in this brief talk, I will be presenting the motivation as to why we are doing this and what we could expect as we mature, and also bring forward some of the challenges that we are currently facing and how probably we could continue to resolve those challenges. So about Akshaya Patra Foundation itself, many of you might be aware of Akshaya Patra, but just to give you a background, it is one of the largest free meal program in India. It is cooked out of a very sophisticated kitchen, extremely hygienic. It's based out of Bengaluru, and it's now spread over multiple locations in India. And one of their core motivation is that no child shall be deprived of education because of hunger. So they do have centralized kitchen, which consumes a lot of heating and cooling also. Heating primarily for preheating systems and also cleaning in place, and also boiler feed water, which is currently used for steam generation, and cooling primarily for commercial office kind of applications and sometimes in the cold rooms. So in this particular project, we wanted to look at how the next generation technology such as the CO2 chiller technology could be utilized for heating and cooling simultaneously. So a little bit of a background about me, as Dr. Pradeep mentioned, I currently focus a lot on development of heat pumps. My objective is to decarbonize process heating. So we have been working on various projects including use of HFCs on delivering steam also for cooking in heat pumps. So we have in fact deployed commercially one of India's first steam generation heat pump in a commercial canteen application for cooking rice and other kinds of vegetables. Similarly, we have deployed a refrigerant-based 120-degree system for automotive component application in near Chennai. Now, our objective is to move away from some of those working fluids. Currently, we use R245FA as a working fluid. It does deliver about 120 degrees C, but the challenge is it is a high GWP refrigerant, and it is also a B2 refrigerant, which comes under the toxic category. So we do, and of course, it's expensive. It's typically anywhere between 50 to 80 euros per kg. And it is also a refrigerant that kind of gets into liquid form as the temperature becomes lower. So it does pose some of the challenges, and we are currently looking at alternatives. And one of the most promising alternative, as you had seen throughout this workshop, is the use of CO2 as a working fluid. Of course, it is benign, 1 GWP, and fairly cost effective. But the challenges have always been that how do you develop a CO2 system that works in a high ambient condition like India? Second, the cost of the system is also fairly high. So the benefits from the system needs to be substantial so that the cost recoupment can be fairly substantial. So that is why we picked up this particular project. And also, since it's a non-governmental organization, it's a trust. So we were able to raise some support from donors to procure the components, and now we are currently putting it together. The OEM that we are working with is Aspiration Energy, who is in the industry commercially manufacturing heat pumps, including the steam heat pump. Of course, IIT Madras and NTNU. I have my PhD scholar, PhD scholar Sandeep Kaundinya, who is working on this system as part of his PhD efforts as well. So here, our objective is to integrate the CO2 chiller and the components, which includes ejector, the excuse me, just a minute. Which includes components such as ejectors, compressors, and heat exchangers, most of which has been procured from Europe, into a system that replaces HCFC, the current HCFC-based cooling system, and also provide hot water. So to do that, currently hot water is being generated using diesel. We are trying to replace it with a heat pump, which can deliver hot water at 90 C, and also supply chilled water at 5 degrees C for space cooling. Here we are doing it as a pilot installation, and we are learning from this installation to optimize on both the design aspects of it and also on the cost aspect of it. So I do like to express my appreciation for Dorin for the compressor, Frigomec for the heat exchangers, and Danfoss for the rest of the components, including ejectors, the instrumentation components, and also the control system. The baseline background, the picture that you see here is the commercial kitchen that you see. Here we have mostly steam temperature is being utilized at 150. So currently we are not in a position to deliver 150. So we are looking at preheating so that we can minimize the fuel consumption. Right now it is at 960 liters per day of diesel. And similarly, the cooling demand is about 17 tons, and which consumes about 22 units of power. So we are trying to replace part of the fuel consumption and part completely replace the cooling capacity by using the CO2 heat pump system. So I would like to draw your attention here that now, even though right now we are focusing on 90, it is possible that we could go to higher temperatures using CO2 heat pumps. Now I have seen there are some approaches that are being developed to deliver even up to 120 degrees using CO2. We are exploring that to see the feasibility of it. And in addition to delivering low pressure saturated steam, our lab is also working on a steam compression mechanism using a rotary compressor based on the Wankel design. So our objective is, once we have low pressure steam, even at 0.5 bar gauge, then we could easily compress it up to the required steam pressure. So the entire system can be electrified in the most cost effective fashion. So that's kind of how we are looking at. The second challenge we normally face in these canteen kind of applications is that the operational hours. So you can look at it, it is fairly restricted between certain time during the daytime. So storage becomes important. So here we are also piloting the thermal storage, which includes chilled water and hot water tanks. So the baseline data from this particular project, while we are designing, this is a time shifted load on the data in terms of both the cooling load and heating load. Now you can understand that the demand for heating and cooling are not concurrent. So there is a nice separation between heating and cooling. So we are integrating a cold storage or chilled water storage tank so that the demand can be met. By way of design, the total heating load requirement is about 306 kW, both for boiler feed water and also for CIP application. And the maximum cooling demand is about 123 kW. So to achieve this, we have designed, in the next couple of slides, I will go into a bit more on the detailed design. To achieve this, we have designed the schematic that you see here based on recommendations and help from Professor Armin. So here we are looking at multiple heat exchangers. One of the core component is the medium temperature separator, where we look at the liquid CO2 that goes back to the LT evaporator. And similarly, we are looking at an internal heat exchanger where we are recovering some of the heat that's coming into the that's from the gas cooler, some of the heat from the spent gas CO2 from the gas cooler into the gas coming into the heat exchanger, so that there is some amount of superheated gas that going into the compressor. So the oil separator or oil filter, the oil circuit is completely gravity fed. So this is one of the challenges that we are currently working with to ensure that oil reaches the compressor completely. So as you go, as I discuss a bit more on the layout of the whole system, you can appreciate that. So here, the primary recovery of the gas cooler, primary use of the gas cooler is to recover the heat from CO2 into water. So one of the key differences that you will observe between a traditional vapor compression heat pump system and the CO2 system is that there is no phase change, of course, in the gas cooler, but more importantly, I can design a single pass system. So I can take tap water or makeup water at 25 degrees C and I can heat it up to 90 degrees C. In some applications, this is favorable, like in this particular case where I can do it as a batch process. But in some applications, this may be an unfavorable condition which we have to work towards. For example, in industrial process heating, if I'm maintaining a bath temperature, a phosphating bath or an electroplating bath, if I'm trying to maintain a bath temperature, the challenge I would face is that I will make up the lost temperature, which will typically be a 5 degree or a 10 degree delta. There, then the CO2 coming out of the gas cooler would have fairly high temperature, which is now rejected into the incoming gas to the compressor. So the efficiency and the COP derived out of such system is fairly low. So there is an opportunity to design systems for batch processes, design systems for small delta T's as well. But as of now, the application that we have picked up is fairly suitable for the high delta T that you can achieve using the gas cooler. The second thing is to improve and to improve the performance and also recover heat, of course, coming from the in the CO2 from the gas cooler, and also improve, also ensure that superheated vapor is delivered to the compressor. We do have the internal heat exchanger. Now, the ejector system, instead of the standard throttling system that is used to recover some of the losses, and also that we are able to maintain the required pressure on the high pressure side. This ejector is a very finely designed component. Right now, it is supplied to us through Danfoss. We are in the process of also understanding the performance of the ejector. So there was an earlier talk, I think, in this workshop talking about ejectors as well. So that's one of the areas that at this point in time, we are not completely focused on in terms of design, but would like to understand a bit more as the project progresses. Now, the other aspect is the empty separator, which is the medium temperature separator. Here, the objective is to extract pure liquid into the evaporator and also improve the heat transfer. Since one of the challenges with CO2 heat pump is also that there is no phase change in some of these heat exchangers like the gas cooler. So the size of the heat exchangers can become pretty large. it will be better if we have a phase change in any one of the processes. So we do look at the empty evaporator to improve the performance, and also introduce pure liquid into the LT evaporator, where I can improve the heat transfer characteristics. So the chilled water system starts from the empty evaporator, and then I have a chilled water output that's coming out of the LT evaporator. So here I can tune the LT evaporator to 5 degrees, and I can tune the gas cooler water output to 90 degrees. So in case of a single, this is achieved in a single circuit without any cascade. So the same thing, if I have to do it in any kind of vapor compression system, I would necessarily have to use a cascade where I would have a high temperature loop, which is basically maybe delivering 90 degree or 120 degree hot water. And then the evaporator of the HT loop would be coupled to the condenser of the LT loop, and the LT loop would be working in a similar 5 degrees to 50 degrees or 5 degrees to 60 degree temperature lift. So this CO2 system completely avoids one full LT circuit. I can do this with simply the ejector and then a clever arrangement of separators. And it also does it at a fairly higher COP compared to the cascaded system. So in terms of energy efficiency, CO2 heat pumps are also much better. And also in terms of ability to deliver a fairly high lift from -5 degree to 90 or 95 degrees, the system works quite well. That's one of the advantages of the CO2 system. So in terms of the mechanism, so in terms of the control itself, here what we have is a two-phase multi-ejector, as you see here, where it controls the high side system pressure by the number of ejector cartridges. So essentially, this is in a cartridge formation. There are multiple ejectors, and by adjusting the number of ejectors that are open, individual ejectors of various capacities can be handled. Second thing is, in terms of maintaining the temperature gain in the hot water, we do have regulating valves or metering valves that allows the temperature to be maintained from 80 to 90 set point, and chilled water between 12 to 7 degrees, depending on the requirement. Now, there is an electronic expansion valve in the LT evaporator, which maintains constant pressure difference of between the evaporator and the receiver at about 5 bar. And the feeding of the medium temperature evaporator, it's entirely by gravity. So there is no expansion device. Now, one of the challenges that you will have is that, especially on the suction side, if the gas temperature goes too low or the pressure goes too low, the limit is set at about 38 bar, which allows, which prevents freezing of waters in the pipes and heat exchanger. Now, we also have a standstill temperature requirement of 40 degrees, which is basically the ambient temperature requirement. In the prototype system that we have at IIT Madras, this is maintained by having a chilled environment, but it can also be maintained by keeping the whole unit at a fairly ventilated environment, so that there is also a pressure relief valve in the system where if the standstill temperature becomes higher than 30, there is a release of CO2 that gets out of the system to prevent any catastrophic damage. That's basically the schematic that you see here. The overall layout of the system is shown here. This is the detailed P&ID that we are currently building as part of the Akshay Patra project. And so I will not go too much into detail here, but it just goes on to say that a bit of careful selection of a couple of components are important. One is the pipe sizes, as you see, because we are relying on gravity separation for removing the liquid CO2 from the empty separator and sending it to the LT separator. So in this particular case, it is important that we do have properly designed pipeline sizes. The second is the allowance for pressure drop. So one of the mistakes we made is having sharp bends in some of these systems when we design the elbows. So there, the pressure recovery is very critical. So you don't, pressure drops and pressure recovery are very critical. So you don't allow any unnecessary pressure drops in the system. Second thing is the oil recovery and oil flow system. Right now, it is also gravity driven. So the proper positioning of the compressors and the oil recovery line is important so that we don't run into any issues of starvation of the compressor. Now, before I go to the calculation, let me quickly show the schematic of the whole system, where you see the empty separator, the whole what I call as the gas cooler and the LT separator. The smaller one is the LT separator, the larger one is the LT evaporator. And there's a door-in compressor that you see here. So here there is a slight amount of angle that is provided for providing the gravity. I mean, each of the heat exchangers are slightly inclined to provide the gravity drainage to ensure that the accumulation and the recovery of oil is more accurate. So to going back to the sizing of the unit, so we decided based on the available compressor, we decided to size the heating at about 141 kW and run the unit for multiple hours. So the requirement of heat is only for about 4 hours. So we can generate the same amount of heat required in operating it for multiple hours, so that I get the 1833 kilowatt hour requirement and the overall heating COP of nearly 3.62. And similarly, I get a good amount of cooling at about 102 kilowatt. The current tonnage requirement was about 17 ton, which is lesser than the available cooling capacity. And in this particular case, as you would all be aware, I don't have control over the cooling output, because as long as I'm generating hot water, I will be generating the cold water. So I might be using it with the overall system here. So the combined COP is about 6.25, and the overall power consumption per day is about 506 units. So with this system, before I go on to the savings calculation, so there is of course the cold water and hot water requirement, and also there is a mismatch between cold water and the hot water demand. So the overall stored energy is about 1000 kilowatt hours. And for this, we have built in a 14,000 liter tank or 14 KL tank, where the total cold water is stored. We don't store the hot water except for a small buffer tank, but the cold water is stored for later use. And of course, as I mentioned, we produce more chilled water than what is required. So if the sources are fully saturated, then we have a mechanism to dump the cooling energy in another location. So in terms of the overall projected saving, currently we are looking at almost this is actually slightly older. Now it's even more increased. This is at about 80 rupees per liter of diesel. Now it's become 95 rupees per liter, and cost of electricity is also quite high. So we are really looking at the reduction in cooling cost significantly, because now you're completely eliminating 17 TRH of cooling load. And in terms of heating, we are significantly reducing it by eliminating the boiler. I am not fully eliminating the boiler. I'm substituting part of the heat requirement of the boiler. So I'm reducing the overall requirement from about 3000 megawatt hours per year to about 2000. So about 30%, 33% reduction. Similarly, if you really look at in terms of cost, I'm reducing the cost of operation per year from about $225,000 per year to about $150,000 per year. So that's a substantial reduction in terms of the heating cost, and overall of a 30% reduction in the cost of operation. This is the OPEX of the system. In terms of CO2 credits or CO2 benefits, we are reducing almost equivalent of almost from about 900 tons of CO2 equivalent per year to about 600 tons of CO2 equivalent per year. And this is primarily by removing the diesel consumption, and also assuming there is the grid equivalent. So the emission factor of the grid is at about 0.7 to 0.75. And this is fairly typical of many places in southern India, where there is a reasonable amount of renewable penetration. And across India, the average is about 0.79. So assuming about 0.7 to 0.75 emission factor of the grid, we are getting almost 300 ton equivalent. This is just one unit. And that is also by eliminating, most of it comes from eliminating the chiller operation. And here we have again considered a small refrigerant leakage. This is typical, but 30% is fairly high. Normally, we don't get that kind of a number, but assuming even that, the CO2 reduction is fairly significant. So now going back to the model that you see here. Now there's a compressor that you see here, there's the door-in compressor, and the channel that you see on the top, that is basically your ejectors, and then you have your both the gas coolers, MT and HT evaporators, and the whole control system that is provided here. The last set of slides, this is currently the status of the fabrication. We are still waiting. I mean, there is some minor changes from the way that we had made in a 3D drawing to the way currently we have implemented it here. But most of it remains the same. There are still some minor components that are still pending, which we are in the process of getting it organized so that this unit can be employed. This unit can be completely deployed and tested. I think that's pretty much it. The last is one of the core challenges that we are facing. Of course, the objective of this particular workshop and the demo projects is towards understanding the challenges in the market. The other big challenge that I am facing right now, even while we are trying to do these pilots and convince customers, even if you are doing free pilots, is the high capex as compared to the traditional or the vapor compression refrigerant system using synthetic refrigerants. Here, capex can be as much as about 3 to 4 times a typical system made out of designed out of synthetic refrigerants. The other perceived challenge is high operating pressure. So I call it as perceived challenge because if the system is well designed, operating pressure should pose no challenge. But when people do talk about system pressure, when we talk about 130 bar, there is a perceived perceived risk on the operating pressure. The other thing that we are still trying to understand, especially in India, because of the high ambient temperature, is the control system, which is a little complex. We're still trying to figure out, and I mean, there is a system that's working in IIT Madras, which we are learning from. But this is also one of the systems which we deployed in the open ambient, not in a controlled environment. So we'll have to understand how the system works and the challenges that might come out. And also the lead time, if there are any small components that are required, is not locally stocked. We do have to get it from the OEMs in Europe. So this allows, this kind of makes it challenging to do a quick turnaround time. So this is what our experience has been in building this unit. But having said that, there are certain good advantages of the CO2 system. Like I said, the ability to do 5° and 95° is a tremendous advantage, specifically in processes that require concurrent heating and cooling. You can imagine dairy processes where I need high temperature hot water for pasteurization, and I need chilled water for the again same process of pasteurization. So right now it is being through fired sources such as coal boiler or other kinds of fossil fired boiler, which the CO2 heat pump system can very easily tackle. So we are talking to a few dairies to understand the process requirement and how to integrate such a solution. And I think, as I said, as we go forward to a higher temperature system and then get into low pressure steam and steam compression, the market that is available for integrating CO2 into industrial heating becomes much larger. So I really look forward to the completion of this particular prototype and see how it performs and how we can now improve the challenges that we are facing, which includes capex, control systems, and also understand how to bring down the production time of this particular unit. So that's all I have for today. Thank you very much for your time, and I'm open for any questions or comments if you have. Thank you.
So participants can raise their hands, so we can unmute and they can speak. They can ask their question, or they simply then write in the chat box. So we have a question from Dr. Tamanjyoti Taluddar. So sir, yeah, you can.
Hello, good evening, sir.
Good evening, sir. Yeah.
Sir, what is the applicability of buffer tank? What is the buffer tank?
Okay. So as I was mentioning, let me just go back to my slide share. See, as you see here, there is a lack of what you call as synchronization on the demand for heating and cooling. So I technically need to then, whenever my heating system is on, my cooling load is not there. So I need to store this energy so that I can use during the off-peak times. And you can also see that during my the load data, where there is load during early hours of the morning when there is no cooling load, and when cooling load is not there, my heat pump is not operational. Whenever my heating load is not there, my heat pump is not operational. So which means that I need to store this energy in a tank. So that is what we call as the storage tank. A buffer tank is primarily where you integrate between the heat exchanger. For example, this water out, I will not be taking to the process directly. I might have a small intermediate tank from where I could take it, so that to ease and ensure that the gas cooler is not starved of water. So that way, just the safety of the system. So that is probably a small buffer tank, but primarily in this particular case, it is for me to handle the cooling unit.
And sir, what extra modification has been done compared to conventional kitchens of Akshay Patra?
Sorry, your voice broke up a little bit. Can you repeat the question?
So what are the major modifications that have been done compared to previous kitchens of Akshay Patra?
No, right now we are not modifying. So if you see here, they still have the diesel boiler. So right now the diesel boiler is used for taking water from, say, where is it? Design broadly. So taking water from 24 degrees to 90 degrees. This is feed water preheating. So now what we are saying is, instead of using the diesel boiler to do this heating also, we are providing it with heat pump. So beyond 90 degrees, they still use the diesel boiler to produce steam. So right now, a portion of the feed water and the supply makeup water that is going into the boiler is being preheated by the heat pump and then supplied to the boiler. And based on which we have almost 25 to 32% of saving in diesel. In future, what we are trying to understand is, once this is done, then we'll probably try to push this up to a slightly higher temperature and then go for steam compression so that I can completely remove my LPG. But as of now, this is the modification. Feed water preheating is done through the heat pump.
By using CO2 as a refrigerant.
CO2 as the refrigerant, correct.
Okay, thank you, sir.
Yeah, Professor Pramod, Sati can.
Yeah. Hello. Yes.
Yeah, you are audible.
So this was a very good talk. So Professor Satyanarayanan. So one question I had was, why is that you have gone for a shell and tube heat exchanger and not a plate heat exchanger? Okay.
So at this point in time, Professor Pramod, one of the apprehensions we had was the stability of the plate heat exchanger at higher pressure. And also it is to do with the, I would say, as I said, components were procured through donors, and it was also one of the leading suppliers, Frigomec, who agreed to supply those heat exchangers. Having said that, I would be very keen on trying my next system using a PHE, because I know PHE has a much higher heat transfer coefficient, heat transfer efficiency and a smaller footprint. So I would like to try, provided there are components that can handle 130 bar.
No, 130 bar is easily, alpha level makes heat exchangers that can handle up to 130. Yes. That's not a problem. But our own experience in building these systems is that you can work with very low split temperatures.
Exactly. So I would really love to explore, especially when I want to go beyond 100 degrees C. I'm really keen to understand PHEs, because with shell and tube, I cannot go beyond 90 degrees, 95 degrees. We would really like to explore that opportunity.
Okay, so that was one thing. Second thing is the oil that gets collected inside your gas cooler.
Yeah.
That what is your plan for oil return?
Right now, we have designed it through a capillary mechanism. So we are going to experiment a bit to see what kind of capillary length and pipeline size that allows reasonable oil recovery. So we are only planning on gravity return right now.
So it will be sucked into the compressor suction?
Yes,
is
yes, yes.
So there is no oil separator as such?
There is no oil separator as such, yeah.
So from the discharge of the compressor, it directly goes into the shell and tube heat exchanger. Can you put up your P&ID diagram?
Yeah, yeah, here. This is my, okay, wait a minute. Just give me 1 minute.
Okay.
So we do have a small oil separator on this next to the gas cooler, I think, but we have, let me go back to the unit that we have deployed. We do have an oil separator. I think this is here. I missed this part. Yeah, we do have a small oil separator here.
So the one that the big black color cylindrical structure is your gas cooler.
That's my gas cooler, correct. Here.
And where is your oil separator?
Let me check. Just a
No, no, on the CAD model only. No, that is fine.
okay, just a minute.
No, in this you also have an ejector.
This is my ejector on the top, yeah.
And your evaporating temperature is 2 degrees Celsius.
My evaporating is 2 degrees Celsius, correct.
And the 2 degrees is just to ensure that you have enough delta T across your shell and tube heat exchanger to have 90 degrees water, is it?
That is pretty much it, yes.
But what about higher evaporating temperatures?
So at this point in time, the evaporating temperature was designed so that I can get a 5-degree chilled water. So we have not really designed it for higher evaporating temperatures.
Okay.
Because there is a chilled water requirement also.
So the oil that is getting collected inside the evaporator is going to be sucked back into the
This
suction
is the
port?
oil separator. Yeah, this one, the one that you see here is the oil separator that goes back into the compressor.
But you also have a reservoir, intermediate pressure reservoir is also there.
Empty is there. There is an empty reservoir, correct.
Okay.
We have 3 heat exchangers. There is the evaporator, the empty reservoir, the gas cooler. The LT, empty, and gas cooler.
Okay. So the system is, when is it expected to be operational?
So we have completed almost all the mechanical components. The electrical components are also mostly there. We still have a few, I think, the oil DP switch and a few components that is expected to be dispatched next week or so. So once that is on, I think we'll be ready. So hopefully another 3 weeks or so.
Okay. Just one last question. Your shell and tube heat exchanger, there is a mandate that it has to be kept horizontal, or it could also be mounted vertical?
So that I don't know yet. So this is something that we had discussion on, but I don't exactly remember why we needed to put it horizontal. This was what recommended by Frigomec. At this point, I did not question. I was told that I needed a small inclination angle for the collection of liquid. So I may have to go back and understand, because this is a question I did not ask.
Sure. Okay. Thanks a lot, and all the best. We would like to see this function. Yeah.
Thank you very much. Yeah.
Yeah, Mr. Santosh Saini has a question. You just
Yes. Hello, am I audible?
Yeah,
Hi.
you can continue.
Yeah, thanks, Professor Sheshadri, for the wonderful presentation. I have a few queries. Like, my first query is maybe or may not be right, but I'm just curious about that. How the pressure in the higher side means in the discharge side control with the help of the ejector, or do we need any back pressure valve as well?
No, ejector itself works kind of like a back pressure valve. If you see, if you tune the ejectors correctly, it works between 2 set pressures. So it is almost like a back pressure valve, or it's almost like a throttle valve. So here, the only difference is you don't have fine control like your throttle valve. So that's why the ejector itself is made into multiple modules. So the way you control flow rate and back pressure is by turning on and off multiple modules. It's almost like a stepped control. So ejector is typically designed for a P in and a P out, and for a P in and a P out, it allows certain mass flow. And we go in stepped mass flows by turning on and off multiple ejectors.
Okay. Okay. My second question is related with your recent publication in Thermal Science and Engineering Progress.
Okay.
So there you presented that best refrigerants using Topsys method in industrial heat pumps.
Yes.
But in that paper, you have not included CO2. So is there any reason for that?
So that particular paper was focused on, say, for example, I have an existing vapor compression system And if I want to consider drop-in replacement for that particular system, so how do I go about selecting a suitable refrigerant depending on the condenser temperature and the capacity requirement and the efficiency of the refrigerant? So that was more focused towards F-gas substitution, no? Based on F-gas regulation. That's more substitution of a like refrigerant. A CO2 system will be something that requires completely a different unit. I cannot use CO2 in a standard refrigeration system. So that's the core difference. So comparing technologies itself, CO2 is a different platform altogether. So we are working on an article that is likely to come up soon, but that is entirely focused only on existing.
So that is for retrofitting only.
Absolutely, retrofitting and also identifying opportunities to switch to a low GWP refrigerant.
Okay. One more question is about that CO2 emission calculations you have presented in one of your slides.
Yes.
So that CO2 emission is TAV, I think, I guess. You calculate total equivalent warming impact. That is
in the paper or in here?
In the presentation.
It is TAV. It is total equivalent warming impact, which includes direct emission because of CO2 leakage and the benefits you get because of substitution. In this particular case, I'm out.
Yes.
Yeah.
Because that that 30% leakages, that is very high. Like in literature, only 10% or 15% is generally recommended.
No, that is very high. In this case, what we have done is, since it's a high pressure system and we don't know that at this point, I don't have experience on the leakage rate and all. So I had taken a double the estimate of typical leakage that we observe and put it as 30%. So as I said, as we gain operational experience, some of these numbers will be revised.
Okay. So, sir, in that, what are the value you have taken that electricity emission coefficient that?
About 0.75. 0.75.
0.75. Because in literature, they used to write that in Indian scenario, because the renewable energy integration is not that much, so they used to take it as 0.9 or 0.95 sometimes.
Depends, no, which geography.
Now the scenario have changed. But
changed significantly. So in India, it is between 0.7 and 0.8, and southern states are slightly better at 0.7 to 0.75. Northern states or northeastern states are more at 0.9. So it's safe because we're going to deploy it in Bangalore. So it's safe to assume that I can still get somewhere around 0.75.
Okay. Thank you, Professor.
Thank you.
Now, next question this from Miss Vanita. So you just unmute and speak, or you just ask your question now. Vandita. Vandita, you raise your hand. Then you unmute and speak just ask your question to Professor. I can see last. Any other question from participants? Okay, if there is no further question, we'll thanks. Yeah, I think we have a question from Dr. Tamal Jyoti. Yes, sir, you can speak with us. Yeah.
Hello.
Hello.
Sir, in this presentation, the quantity of chill water is a bit lower than that of hot water.
It will be. It will always be, because if you really look at it, if you measure the COP of the system, it is the heat load of chilled energy plus the power input will be the hot water. So hot water will always be higher. If you look at a conventional, any kind of refrigeration cycle, the evaporator load plus the energy that you input to the compressor will be the condenser load. So obviously your chilled water quantity will be lower than the hot water production.
Okay.
Okay, so if there is no further question, we'll thank Professor Sheshadri Satyanarayanan for his excellent talk on the HeatPump Foundation and discuss about the requirement and the application of CO2 in the these application. So, and this also ends the session today. So we'll meet up tomorrow again for the this session again. Siva, it's over to you now.
So we are finishing 3 sessions. So at the same time tomorrow, 4 o'clock, we will meet again. So you can leave.
Thank you. Thank you very much.
Thank you.
Thank you all for your time. Bye-bye.
Thank you.